Assalamualaikum and greetings. For our Chemical Engineering Integrated Project September 21 semester, we are from Group 6 FOsSIL consisting of Jashmen Reuben, Agathiyar Varman, Muhammad Iman, Nur Fatihah and Ainur Farissa are required to produce a palm oil-based biodiesel plant. And for our problem statement, Biotenaga Sdn Bhd is currently looking to hire a team of engineers who are passionate and skillful to design a reactor separator system for conversion palm oil resources to 3,000 tonnes per year of high-quality biodiesel. The produced biodiesel later will be sold to other companies for mixing with petroleum diesel. And in this project, we are utilizing glyceryl tripalmitate with methanol to produce methyl palmitate, which is our biodiesel. I will now pass the presentation to the next presenter.
Assalamualaikum and hi, I'm Nur Fatihah. I'll be starting today's presentation with the introduction of the reaction that is taking place. For the reaction of biodiesel, the reaction involved is transesterification. This reaction converts triglycerides in palm oil into fatty acid methyl ester as the desired product and glycerol as the byproduct, as you can see in the slide. The alcohol will then utilize methanol. Moving on, transesterification's reaction is an overall process, is multiple reactions that consists of side reaction that produces intermediates such as monoglycerides and diglycerides. But according to the research of Narvaez and the team, it is found that at an optimum molar ratio of alcohol to oil, the side reactions are highly negligible and the intermediates are diminished. So, our project utilizes optimum molar ratio, so there is only a single reaction is focused, which is 1 mole of triglyceride should react with 3 moles of alcohol to produce 1 mole of glycerol and 3 moles of methyl esters. Next is the overall process flow diagram. The diagram here shows the whole plant of the biodiesel production that is proposed by our group. As you can see, there are 2 CSTRs that are arranged in series and 4 separators that separate the glycerol. Recover the methanol to be recycled and wash the biodiesel with water to remove impurities and finally evaporate the biodiesel to get high quality concentrated biodiesel. That's all from me. I will pass the floor to the next presenter. Thank you.
Hello everyone, I'm Jashmen Reuben and I'll be explaining the reaction engineering part. As said earlier, the reactor used is CSTR, and this is because it allows continuous production of our product, which is biodiesel, and most importantly, the reactor allows control in general to gain fast response to the changes made in the operating condition. Talking about the operating conditions, the CSTR in series operates at 170 degrees Celsius isothermally. The high temperature and pressure are because in this project we utilize supercritical methanol, and because of that, we also do not need a catalyst. Most importantly, the methanol to oil ratio is at optimum level of 6:1, that ensuring the side reactions are negligible. Furthermore, the selectivity and the yield of the biodiesel of the desired product are 3. To further increase the selectivity and yield, high temperature can be utilized. Moving on to how the design reactor system made the productions. Firstly, the utilization of CSTR in series provide lower production costs and a more uniform product quality. Secondly, higher operating temperatures causes the reaction to be completed faster and a higher yield of biodiesel obtained. Next, sufficient reaction time gives a higher yield of biodiesel. And last not the least, optimum alcohol to oil molar ratio provides further improved yield of biodiesel. Lastly, using the 5 steps of isothermal reactor volume evaluation, the volume of both CSTR is to be found as 1000 liter and the space time is known to be 1.06 hours. That is all from me. Thank you. I'll pass the floor to the next presenter.
Hello and Assalamualaikum. My name is Muhammad Iman with ID 190000691. Now, I will continue the presentation with process modeling and simulation part, where the simulation of the reactor is performed. We have done the simulation using symmetry software. For the simulation, we have used the glyceryl tripalmitate as the reactant, and the main reactions that happen in this simulation is transesterification with chemical equation shown in the slide. The substance that present in the simulation are glyceryl tripalmitate, methanol, glycerol, and methyl palmitate. This is the picture of completed flow diagram that we have done to simulate the reaction process using symmetry software. After that, we have done comparison between simulated concentration and manual calculations concentration. The formula of percentage error is shown there, and we have calculated percentage error between manual and simulated value of concentration for each components in both reactors as shown in the slide. We also have done sensitive analysis. From the graph, we can know that final oil flow rate will not be affected by changing the feed temperatures from 10 to 100 degrees Celsius. This is because pump oil will still be heated to 170 degrees Celsius in both CSTR to achieve maximum conversion. Next, we can see that final oil flow rate gradually increases as the oil feed fraction increases from 0.5 to 1. This is because greater feed fraction means greater amount of feed pump oil, hence more pump oil will be left unreacted after the reaction has completed. Lastly, we can see that final oil flow rate gradually increases as well as the oil feed flow rate increases from 0.5 to 2.3 km per hour. This is because higher flow rate means more amount of pump oil will be entering both CSTR and more pump oil will be left unreacted. That's all for process modeling and simulation part. Thank you very much.
A very good day to sir and madam. My name is Agathiyar Varman and I will be presenting about separation process 2. First, this is the block diagram where the separation unit used is the evaporator. The separation technique used is the evaporation process. The main objective of using an evaporator is to concentrate the biodiesel solution by removing the water vapor components from the biodiesel solution. This is achieved by vaporizing portions of water components from the biodiesel. Therefore, the biodiesel becomes more concentrated and viscous. Moving on to the type of separation unit, which is the falling film evaporator, and this is the schematic diagram of it. Falling film evaporator is chosen because it can handle high viscous solution. The falling film evaporator has an excellent heat transfer rate compared to other evaporators, making it very efficient, producing clean and concentrated biodiesel. Thus, selecting a suitable and efficient separation unit leads to quality separation process. Quality separation process leads to quality biodiesel production. Moving on to the material used for this separation unit is the stainless steel, because it has excellent corrosion resistance, high temperature resistance and low maintenance. One of the important configuration is the spray nozzle, which is an equipment that improves the distribution of biodiesel feed at the top of an vertical heat exchanger. The next part is the mass and heat balance calculation, starting with the assumption as shown in the slides. After that, by using the formula of overall material balance and solid balance, the mass flow rate of concentrated biodiesel solution, which is 830 kg per hour, and vapor flow rate, which is approximately 19,000 kg per hour, is found. By using the heat balance formula and by substituting the value of latent heat of steam and enthalpy of vapor found from the steam table, the rate of steam is found to be approximately 25,000 kg per hour. Then the steam economy is found by dividing vapor value with steam value, and we will get steam economy of 0.8 for this evaporator. Finally, rate of heat transfer is found to be approximately 12,800 kW. That is all from us. Thank you.